So today our topic is computer arithmetic, and we have already discussed this in the classroom, but due to insufficient number of students, again we are discussing that. So if you have any doubt in any stage, just tell me. Okay, so I will try to clear your doubt, but for now that is the topic, computer arithmetic. So computer arithmetic means how computer actually stored the data and how it will evaluate the data according to the computer interface or the storage interface. So basically you are in 5th semesters, all of you are in 5th semester. That means you know about that very well, that there are some format or number system with which computer store the data. So first of all, to store the integer type of data, which type of number system used? Is there anyone who can say that I want to store integer numbers? Then which type of number systems or number format I will use? Is there anyone who can say that to store integer type of number? Type of number. So to store integer types of numbers, computer generally use the fixed point number system. Fixed point number system. So in this fixed point number system, so suppose you have a 32-bit machines. You have a 32-bit machine, suppose. So in this 32-bit machines, that means each of the bits you have 32 boxes where you can fill the zeros and 1. So suppose if you have 32 such type of boxes and you can put here 1, either 1 or 0, then how many numbers you can build? Can anyone say? Just use the permutations concepts.
2 to the power 32.
Ekdam, 2 to the power 32. So that's why we can 2 to the power 32 different numbers actually we can stored in this 32-bit system, number systems. But the problem is, actually if we allow the negative signs, that means allow the sign also, that means it can store the positive signs and the negative signs. So obviously one bit occupied by this sign. So in that case the total number range, so range of the fixed point number, range of the fixed point numbers in this 32-bit systems is minus 2 to the power 31 less than or equal to, suppose the x, and less than is equal to 2 to the power 31 and minus 1. So that is the minimum range that you can store in the fixed point number system in a 32-bit machines, and that is the max number 2 to the power 31 minus 1 that you can store. If it is a 64-bit machine, then you will get in 64-bit, if you take that 64-bit, it will be minus 2 to the power 63 less than or equal to x and less than equal to 2 to the power 63 minus 1. So that means in any n-bit machines, if you save the fixed point number, so you will get minus 2 to the power n minus 1, and that less than equal to x and less than equal to 2 to the power n minus 1 minus 1. So that is the ranges of the numbers which you can produce in a 32-bit machine using the fixed point number system. But the problem is, if you take the 2 to the power 31, these patterns, so this 2 to the power 31 I think near about some 2.1 into 10 to the power 9, that is the number. So it is not a very large number that you can store in a machine, and that's a problem. So in this fixed point number system you have a limitations. If you want a larger number than that number, so you can't use it in a 32-bit machines. You can bring a 64-bit machines or more than to store the number, but it is also not sufficient. So that's why we need a different types of number systems which can hold the real numbers, or which can hold the numbers in the real number formats. And which type of number system store the real numbers? So one type of fixed point number system. What is the another type?
Floating point
Ekdam, floating point numbers. You all know that you have already programmed the C programmed, and where you use the integer type of data and float type of data. So integer type of data, that means the fixed point number system which store the integer values, and that float system which saves the real types of values, and that is the second types of pattern which is called the floating point system. Floating point number system. So in the floating point number systems is actually same as our scientific number systems. Like if you use the scientific mode in your calculators, and if you have a suppose a large number of such types, so it will gives you some 2 into 10 to the power of some values, na? 4, 5, 6, 7. So now you can see that this large number is now actually stored in this type of small formats. So that's why if you have limited space also in your calculator, suppose in your calculator in the display there are only 8 or 9, so without reducing the values or without chopping the values, it can show you the full values. So that is the advantage of the floating point number. So suppose you have a large number and which have suppose 100 bits, so at least it can gives you the first number. Suppose your number is looks like that A, B, C, D, and that's why it will continue. Or if you take the numbers, so suppose it is continuing like 2, 3, 4, 7, 5, 3, 2, 1, 4, and in this way it have 64 or suppose 90 numbers, 90 digits. And in your calculator there are only suppose 8 bits to show. Then if you use the fixed point system, so it will chop after the 5th digit, 1, 2, 3, 4, 5, 6, 7, 8 digit, and after that you can see the whole number. So how you will predict that how many digits are there, 90 or 80 or 70. So here the at least approximately floating point number system helps you, that it will gives you that 2.3475321 or some values after that e of sum or 10 to the power that 90 in this format. It will gives you the value. So now you can see that how many total digits are there in your number and how large your number is. So that's why every floating point number systems actually looks like a x is equal to some plus minus z. If I say it is a binary machine, suppose binary machines, so it will be some z into some 2 to the power of p. So this z is called the mantissa of the number, and this p is called the exponent. So in a decimal systems, so here you will get 10 to the power some values. In the binary system here the base is 2, so that's why we have 2 to the power p, and here z is the mantissa. So obviously in the binary format you will get some 1, 1, 1, 0 in this type of mantissa, and basically we use the normalized mantissa here. So when we say a mantissa normalized, so a number x is normalized if this z value is in between some 1 and 2. If you take it as a general value, that means some 1 point something, 1 and less than 2. So that means if this is a binary number 0.001 010101110, so this is not a normalized value. But if you shift the point from here to here, there actually, So then you will get some 1 point some 0 1 0 0 1 1 0 and into that 2 to the power minus of 3, because you have shifted the point 3 steps in the right directions. So that's why we have taken the 2 to the power minus 3 here. So now this number, these presentations of mantissa actually a normalized mantissa. So whenever you will use the normalized mantissa, so basically you need a 1 at the starting points. So whenever, that means like the first significant digits, because here this 0 0 these are not significant, so we need a significant digits. So like the first significant here, this is 1, so you have to shift the point from the starting point to after that 1. And now this type of presentations where this z is belongs to greater than equal to 1 and less than 2, and then we call this the normalized mantissa. Is there any doubt about the normalized mantissa? Because whenever you want to save a data in the machine format, you need to first express it in the normalized form and then we save the mantissa portions. How we will save? We will show it here. So up to now, is there any problem? If no, then we will continue to the next sections. So now how to save the numbers, that is another thing, and what is the actually format of the numbers. So basically this is the floating point system. So in the floating point system, one sign will be there, then one mantissa portions will be there and another exponent portion will be there. Now if you take the typically one 32-bit machine system, which is called the single precision actually machine, so or single precision format. So in single precision format, where it will goes, in the single precision format, if you take in 32-bit machine, in that means in 32 bits sections, in 32-bit system, basically 1 bit, this type of 1 bit is preserved for the sign, only 1 bit preserved for the sign only. Then after that, here total 8 bit 1 2 3 4 5 6 7 8 1 2 3 4 5 7 8, total 8 number of bit is for the mantissa portion, not for the mantissa, which is the exponent portion. And after that, the remaining 23, whatever, maybe there are many boxes, so others 23 bits are for the mantissa portion. So that is the format for the 32-bit systems, and in this way it saves the number. So if it is a positive number, then what is the sign bit? Is there anyone who can say that? What is the sign bit for the positive number?
Positive is 0, negative is 1.
For positive number it will save 0 and for negative number it will save 1. This is the second. Now if you see the 8-bit exponent portion, so here it will follows the fixed point number system, and in the fixed point number system, in a 8-bit system, how many total numbers you can save? So it will be total 2 to the power 7 minus 1 and x, and is then equal to 2 to the power what? 7. Total how many numbers will be there? Is there anyone who can say that? Just calculate it. What is the 2 to the power 7 values? Minus 128, na?
Minus 128 to minus 127.
And less than equal to 127.
127.
So that is the range of exponent, but basically in the IEEE if you take the IEEE 754 format, which is a actually widely used format, in this IEEE 754 format, this exponent portions only allows you from minus 126 less than equal to x and less than equal to 127, and these 2 bits are actually reserved for 2 special numbers. So 2 bits, these 2 actually bits are reserved, or 2 locations you can say, corresponding to 2 locations. One is corresponding to all 1 and another is corresponding to all zeros, and these 2 numbers actually the saved for the or reserved for 2 special number. And what are these 2 special numbers? So one is the INF. This INF, sometimes it is plus INF or minus INF, that means like the infinity. So when it occurs when the overflow error occurs actually. When the overflow actually occurs. Overflow means you have a 32-bit systems and you have a large data, and which is actually beyond the capacity of that system. So in that case it will treat it like infinity, and it will show that INF in the system. And similarly, if you take the division with 0, you will know that it is undefined term. So in that case it will gives you NaN, which means the not a number. So these 2 are reserved, these 2 locations actually reserved for these special characters. But otherwise it can gives you minus 126 to 127. That means now your range is actually much larger than the previous. Previously it will be minus 2 to the power some 31 or this type of values, but here you have 2 to the power minus 126 and here 2 to the power 127, and this value is much larger than the previous. So you can store more data in this file system or number system format. So now the question is, what is the format for the 64-bit machines? So if you take the double precision format, that means if you take the 64-bit system, so in this 64-bit system, again the 1 bit is reserved for the sign. Then after that here total 11 bits are there. 11 bits are reserved for the exponent, and other total the remaining, I think how many remainings are there, 52 bit, these are for the Mantis. And here the exponent, range of exponent is actually, is minus 2 to the power, you have 11 bits, that means you will get 2 to the power 10 less than or equal to x, and here you will get 2 to the power 10 minus 1. So what is 2 to the power minus 10 here? 1032. কত হচ্ছে দেখো তো, 1024 না I think. So that means 1023 less than equal to x and less than equal to minus 1024. And basically again the 2 in IEEE 754, it will allows you only minus 1022 less than or equal to x and less than equal to 1023. That is the system. Okay. So that is the ranges. That means in double precision system you can store from 2 to the power that minus 1022, it is very small value, and also largest value 2 to the power 1023, it is also a very large value. It is actually near about 0, tending to very small, and if you take 2 to the power 1023, this is very large values. But here in the IEEE format, if particularly no format is given, then basically in this format, IEEE 754 format, whenever you save a values, it will only take the portion after the point from the mantissa. So suppose in a number after the conversions you have a mantissa, this type of mantissa, 1 point normalized mantissa 1.00010210 not 2 1101, this type of mantissa you have. So basically in IEEE 754 it always saves only these portions in the mantissa part, not with the 1.0, because it always first convert it to the normalized form, and you all know that in the normalized form this pattern is same always. So that's why automatically assume that there are 1 point before that mantissa, and it will saves only that portion 0001 011 01 in the mantissa portions, and in this way it can takes one more number in its system. So that means if it is a 32-bit system, it can save one number in this type of actually tricks, with this type of tricks. So in a 32 bits, it's just like you are saving 33 digits. Like in 64 bit, you are like saving 65 bits here. So it is another trick. So if no particular format is given in your questions, and if it is a standard IEEE 754 format, then only the after the point part is saved in the mantissa portions. And here the another problem is, in the exponent there is no sign, in the mantissa there are signs. So if your if your actually numbers have a negative sign, so you can just give here 1 bit corresponding to negative and 0 corresponding to positive. But the problem is, suppose your number is very small, like 2 to the power suppose -12 or 2 to the power -13, this type of part is there. Like this, your number is 0.000000 and then 1010101. Whenever you make it a normalized form, it will gives you 1.010101 into 1 2 3 4 5 6. So after the 6th place means 2 to the power minus what? 6. Now here you can actually 1 minute. I have closed the is the screen visible again?
Yes, sir.
Okay.
Yes, sir.
So now if you see this number, now this number is 1.010101 into 2 to the power minus 6. Now as per the IEEE format, just save this portion in the mantissa part. That's okay. But the problem is, what about the exponent? So here the exponent is minus 6. That means the exponent needs also negative sign, but there is no allocations for the negative signs because the exponents have only 11 bits and all for the numbers, and that's a problem. So that's why in IEEE 754 format, actually particularly for this format, we use the biased exponent form. Biased exponent, that is very important, huh? So what is biased exponents here? So biased means, suppose you have minus 6. Now what is the minimum number of exponent actually you can have in this system? If it is a 32-bit system, so minimum you can get minus 126 as per the IEEE format. If it is a 64-bit, you can minimum get minus 1022. Here in this way you can get minimum, suppose minus 126, that is the minimum number. So for the biased exponent in the 32-bit system, we will add with 127. That is the adding factor actually. Always, whatever the negative sign comes, just add it with 127 and it will make it positive always, because the minimum negative number what you can get is minus 126. So that means if you take a sum with 127, it will be positive, and then convert it and save it. And Again, when you extract the values, machine again when extract the values from binary to decimal, after calculating the exponent portion, it will subtract by 127. That means whenever we want to save the data, whatever be the values, we add with 127 and then we convert it to the binary and then we save. And in this way you can cope this negative problem, negative exponent problem. And if it is a 64-bit system, then add with 1023, because here the minimum negative is 1022. So now, this is the 32-bit system. In 32-bit system, just add it with 127, and if it is a 64-bit system, then with -6 add 1023, and it will make it positive. And after that we will save the exponent, and that's the process. So whenever a number comes, first make it binary and then make it normalized form. After making it normalized, we will save the mantissa portion, and whatever the exponent, add 127 if it is a 32-bit system, and add 1023 if it is a 64-bit system, and after that convert it to the binary form, not before that, and then save the values. So it will be better if we take some numbers and if we convert it in the 32-bit system or in the 64-bit system.